So I'm just going to talk very briefly about space in the chamber and segue that into the space sub-panel, which is about hydrogen in the space sector. So I wanted to just quickly touch on a concept that's been mentioned a number of times today, and that is the will to change. So we keep talking about knowing what we want our future to be with our technology. We know that we want Industry 4.0 to make our working life better. We know that we want decarbonisation. We know that we want to go to space. How do we get from where we are to that point? And that's something that the space sector inspires me all the time. And with these other peripheral industries that I'm learning about through the chamber, inspires me to keep trying new things and keep striving for that future that we're imagining. So Jens Gernemann this morning explained that there are 6 manufacturing key industries for Australia, and 4 of those are clusters of the chamber, as you've heard today. The 5th one is space, so it's actually quite important to the chamber as well for our strategy. And not only that, but it connects into the other clusters, into the other industries that we have. So just as some quick points about the other clusters, the health cluster, space does microgravity medical research and pharma production. In mining and resources, there is extraterrestrial resource extraction and in situ resource utilization. So going to other places and mining there, and then using the resources in that place to further travel. GPS navigation in agriculture is also important for our industries. And then energy systems, such as propulsion, batteries, solar, all been part of the space sector. And so finally, the chamber actually has members already in its group that do space industry work. Some of those, one particular mention is hypersonics that does scramjets in Australia. They're researching how to produce scramjets in Australia, and they're going to use green hydrogen propulsion for that. But a couple of ones that were mentioned by Bronwyn Fox already earlier today, she mentioned Cablex. They were recently a member. I'm not sure if they still are, but they were part of our group. Airbus obviously is a big one. And Roda and Schwarz. BASF has space capabilities. And there's many others. So why this panel? So I came to the chamber to work in the energy cluster and as the space coordinator, and I've been trying to fuse those 2 parts of my job together, and this is the product of that. So nearly a year ago, I heard about Fichtner from Germany working with DLR on their hydrogen propulsion systems, and I've been hoping for this moment to come since then. So we're going to talk about hydrogen in the space sector, the production of hydrogen fuels from solar thermal technology, and we're also going to talk about hydrogen storage in aerospace and space. So I'm going to introduce my first panelist who will speak for 5 minutes about his company and his work, and that's the Managing Director of Fichtner Australia and New Zealand, which is Dr. Florian Klumpp.
Thanks a lot, Thomas. So is that the microphone? Yeah, good. So thanks a lot for the introduction. I'm honored to speak here today. And I was asked, or Fichtner was asked to hold a presentation because we've been active working with the German Aerospace Center for many years. And often in the field of hydrogen, they actually claim to be the world's or Europe's greatest hydrogen consumer. And just to mention a few projects, not going to read through all of that. We've been working at the construction of the upper stage testbed for the Ariane 6 rocket in Lampoldshausen, close to Stuttgart. Also on the hydrogen infrastructure and compressor station design for the hydrogen supply on that large site with all the testbeds. And actually, my first job, my first project when I started with Fichtner some 9 years ago was on the utilization of a local wind farm to produce green hydrogen. And well, we heard that, isn't hydrogen green? Well, if you ask 100 people out of the street, they associate hydrogen with renewable, sustainable, modern, environmentally friendly. But it's actually not. It's not the full truth. We've got quite a lot of colors for hydrogen. Heard that in the other presentations. Most people think of hydrogen as green, and that is where we're all aiming towards. It's the water electrolysis based on green electricity from renewable sources. But the truth is that the vast majority, the biggest share of hydrogen today is produced from natural gas by steam reforming, so not green at all. This is what we refer to as gray hydrogen, and we already heard about blue hydrogen, kind of capturing the CO2 emissions and to take them away. And there are other forms like black or brown from coal and some other fancy colors such as purple or pink if nuclear power, for example, is being used. The bottom line basically is, as said, hydrogen today is not green. It's made out of natural gas in most cases, and less than 0.1% globally is actually produced with renewable energies. So really the bottom line is hydrogen is not necessarily green, and neither are commercial space flights. So just tackling on that, and that raised a few questions, and on newspapers asking questions such as on the environmental payload of space tourism. Not very good news. If you try to position your modern space flight for very rich people as modern and technology advanced, and they made like comparisons, and they compared a rocket flight with Virgin Galactic to the edge of space compared to a conventional aircraft flight, and it's about 60 times more, has a 60 times higher carbon footprint per mile. And that made these big companies to reconsider their strategy. For example, Blue Origin, Jeff Bezos, with their new engine, New Shepard. It's now working on clean liquid oxygen and hydrogen. They claim there's no carbon emissions anymore, and they significantly reduce the CO2 emissions compared to the original use of conventional fossil fuels. SpaceX, a bit the same. They used to use kerosene-based fuel in the past, and now they changed. They developed a new engine called SpaceX Raptor, which uses a liquid, very cold methane, and they announced a project in Texas. They claim to be the world's largest, a lot of companies do that, claim. They claim to be the world's largest hydrogen project. Well, it's quite big, 60 gigawatt. Well, this is what they aim for or plan, 60, not megawatt, gigawatt, and they want to supply clean rocket fuel for Elon Musk. So they clearly see they need to kind of address this carbon footprint. And coming to a summary, as I only have 5 minutes, what are the key takeaways? 1 point, currently hydrogen produced is not green at all in most cases. Commercial space flights start to reduce CO2 emissions and try to be more sustainable. Hydrogen is still expensive. We already heard about that. I worked in quite a lot of hydrogen projects in the past, and a lot of feasibility studies and open and conceptual design studies, and open speaking. Hydrogen projects aren't no-brainers at the moment. Technically, it's working, but from an economic point, it is a tough one. And one of the takeaways I learned in these multiple projects I worked for, that sophisticated, really thorough optimization of the entire hydrogen value chain is needed to make these projects fly. And it's the money at the end of the day that makes the technology successful. And optimization really is a key. I've seen a lot of companies optimizing the electricity supply of renewable energies, and then the hydrogen production itself, potentially attached to liquefaction or an ammonia production, and then the demand separately optimizing that. It's not working. You're losing a lot of potential savings, and that was basically the idea why we as Fichtner developed the Fichtner Hydrogen Optimizer. It's a software tool optimizing the entire value chain. All right, that's from my side. Thank you very much.
Hello? Oh yeah, so I just wanted to quickly say, Florian keeps completely downplaying the capabilities of Fichtner in hydrogen propulsion for aerospace, because there are very few rockets in the world that have the capabilities that the Ariane series does in terms of how much payload it can take into orbit. Australia has never even made anything close to the size of that. And they have been working for 3 decades in building the hydrogen propulsion systems for the testing site for that launch vehicle, which is very impressive. So, privileged company we have. And I would like to welcome Dr. Wojciech Lipinski onto the stage to give his presentation. He's an academic of multiple institutions around solar thermal production of power, fuels, and material, in particular hydrogen and renewable fuels. Thank you.
Good afternoon, everyone. Thank you, Thomas, for the introduction. So today I would like to tell you a little bit about renewable fuels for aerospace. Basically, the history of aerospace is the history of combustion-based propulsion. There are piston engines still run on leaded gasoline. There are different types of turbines. A jet turbine is a masterpiece of engineering. It has been optimized for more than a century now. And there are some rocket engines, the old dirty pulse jet engines. Basically, they shouldn't be avoided, and they are almost eliminated. And then we have rocket motors and engines, those running on solid fuels and those running on liquid fuels. Now, the key fuel that is used in the aerospace sector is the jet fuel, and based on kerosene. Kerosene is a hydrocarbon, a mixture of hydrocarbons. There are different standards, but the requirement for the jet fuel based on kerosene is to have certain physical properties, such as the freezing point. Now, there are jet fuels, Jet A, Jet A1, used around the world depending on the climate zone. Jet A1 is more suitable for harsh conditions. And most of these fuels is produced these days by refining petroleum. Now, there is also a growing market of synthetic kerosene made from synthesis gas, but this synthesis gas comes from fossil fuels. And today I will show you that we can do it actually the solar way, clean way. We can have green kerosene with an example of recent developments in Europe. When we burn those hydrocarbons, we produce carbon dioxide. About 2.5% of all anthropogenic emissions are due to combustion in the aerospace sector. There is also water produced, which forms the condensation trails, which is kind of a pollution in the atmosphere. Nitrogen is there because we use air. When air is oxidized, we can form NOx, which is undesired. So we should avoid this one. And the product is the heat, which is what we want for propulsion. Now, something happened here. So let me quickly go through this. Let me start with the various alternatives, how we can decarbonize the aerospace sector. Number one, we can use fuels that do not contain any carbon, for example, hydrogen. And thermodynamics will tell us, I used to teach thermodynamics for many years, so that's why the plot is there. We can make the hydrogen at low temperatures, and then we need mostly electricity. This is the basis of the low temperature electrolysis. This is what is state of the art basically already. But there is one caveat here. The efficiency is not yet what we could achieve. We can then go up with the temperatures, and we can use high temperature electrolysis, which gives us higher efficiency, but at the same time it's not yet as mature as low temperature electrolysis. And there are other processes I'm going to mention soon. Now, hydrogen has been demonstrated in the space sector. It took humanity to the moon. There have been a number of aeroplanes run on hydrogen, experimental ones. Throughout the Cold War up to the present days. For example, there is a project by Airbus to demonstrate hydrogen in Airbus A380. And another development, joint development between DLR, or German Aerospace Center, and the Slovenian company Pipistrel. In this case, we don't have combustion. We have hydrogen used to generate electricity in a fuel cell that drives electric motors. Now, another Carbon-free fuel is ammonia. It was mentioned today. Ammonia was demonstrated for aircraft, military aircraft by the US Air Force already some time ago. It is produced by the Haber-Bosch process worldwide. We need hydrogen to make it. Yet another fuel without carbon is hydrazine, and this is a poison. It's a highly toxic material. It is used for power rockets, especially in military applications, and it is also used as a niche fuel in some military aviation applications, but it is undesired for its toxicity, for the environmental impact. And then we have hydrocarbons. We have hydrocarbons in aviation, as I mentioned, kerosene, jet fuel, and also in aerospace. Kerosene is used in aerospace. Apollo 11 used 20 tons of kerosene per second on launch in the first stage. Hydrogen was used in the second and third stage. So there is a large amount of kerosene used in aerospace. Or hydrocarbons such as methane, the engine Prometheus by Ariane. Now, if we replace the carbon in hydrocarbons by renewable carbon, then we can close the carbon loop, and actually such hydrocarbons will be renewable. There are two basic routes. One is to process biomass to hydrocarbon fuels. So in that case, biomass captures CO2 from the air, and later on, when the hydrocarbon fuel is used, this CO2 ends up in the atmosphere, but it is taken again by the biomass. We close the carbon loop. Another way is to do it the more engineering way, which means we engineer systems for gas separation, for direct carbon capture from the air. This CO2 and water are then split in thermochemical cycles, thermochemical processes, or high temperature electrolysis. Here is one important information. There is a lot of there are many studies on electrolysis of water. CO2 electrolysis is extremely difficult, and that's why electrochemistry for CO2 splitting is not the best route right now, at least. So people talk about thermochemical cycles. And this is what has been done now at ETH Zurich. ETH Zurich, in tandem with their startup companies Climeworks and Synhelion, developed a system which takes carbon dioxide from the air. Climeworks commercializes their air capture system. It also takes water from the air, and the concentrated CO2 and water are passed to a solar reactor, which reduces them to make synthesis gas, and then we can obtain, for example, kerosene in a gas-to-liquid process, which is typically the Fischer-Tropsch process, also invented in Germany. So they use a thermochemical process based on cerium. Cerium is not as common as iron. It is actually an rare earth, but it is relatively cheap and still abundant. Now, they first developed a reactor to split CO2 and water using these porous cerium dioxide structures, demonstrated on the roof of ETH, mechanical engineering of ETH Zurich. And now they scale up the system to 50 kilowatts on a tower at IMDEA in Madrid. The whole cycle has been demonstrated, and the cycle is powered just by sunlight, takes air, no water, no CO2 from all other sources, and produces kerosene. And the results have been just published in Nature. So it is an alternative route to pure hydrogen propulsion, and I believe, personally, hydrocarbons will be there for long-haul aviation and for critical heavy-duty space applications. Thank you.
Thank you, Wojciech. So one of the issues that's been mentioned already with hydrogen and aviation is the fact that hydrogen has great mass per unit energy, but very poor volumetric volumetric unit energy. So Dr. Jehan Kanga's startup is working on a way of storing hydrogen in metal organic frameworks, which increases the volumetric density of stored hydrogen, and he's about to give his presentation for us.
Cheers. Thanks so much, Thomas. It's really great to be here. We're a tiny little startup, so it's a great honour to be on the stage. Just a bit of background. I was originally a chemist with University of Sydney, spent 5 years with KPMG, did a whole lot of stuff over there, and then decided that I wanted to jump right back into hydrogen, which is where the original research was going back to 2010. So we've talked about where hydrogen can be used, and it's what we're focusing is on what we call the no regrets applications of hydrogen. So looking at trucking and aerospace and space, they all need hydrogen. They cannot be, you can't use electrification for a lot of those applications. Now the big issue, the big elephant in the room is really around this unsolved challenge of volumetric efficiency. So that big white tank, it's 4,500 litres, that only carries 10 kilograms of hydrogen. This is actually ATCO's Jandakot innovation site over in Western Australia, the very first refuelling site in Australia for the Toyota Mirai program that got launched late last year. So our job at Rux, we're actually going to replace that tank, and we're going to put our materials in that tank and increase the volumetric density of stored hydrogen in a dispatchable context. So we're not going to convert the hydrogen, we're not reacting it in any kind of chemical way, we're using adsorbent materials. It's very, very relevant in the aerospace and space climate, and as you can see, this is the very first manned aircraft ever to run on pure hydrogen. Zero Avia's test flight from last year, most of the fuselage is tank. And that's not very useful, if we're thinking about Airbus, which plane have they picked for their Zero-E program? The A380, because they're looking for as much space as they can possibly find. And they're using liquefaction, right? So they're at very, very high densities, and you pay about a 44% penalty. So you're using up 44% of the total energy content of the hydrogen just to get to liquefaction temperatures of minus 253 degrees Celsius. So liquefaction is a pretty difficult process. So what we're doing is we take metal organic frameworks. These are a new field of materials that have been worked on primarily in the US, Australia, and in Europe since about the early 2000s, and there was a lot of work done in hydrogen storage in that period and under George W. Bush and later under the Obama administration, which is when I did my PhD, and then everything sort of went cold because hydrogen sort of became uncool. But now it's cool again, and we're back, and it's very exciting because actually some of the materials that we've been working on are really dirt cheap, right? So we're actually in hybridizing our materials with composite tank materials. We're actually going to accelerate the learning curve around how cheap these tanks can get and really bring down the cost of those tanks. And that's really important for adoption. The storage takes up about 20-30% of the total cost of any kind of application vehicle, and so we need to get that right down because we need fast adoption. And we need fast adoption because we're in a really big race, right? And it's not a race against other storage applications like ammonia, or it's a race against the climate, and we need to get things really moving very quickly. So a really important aspect of all of the different kind of storage technologies that you might hear is actually how these can be used. Some of them are dispatchable and can be used straight away. Some of them require huge chemical plants to actually convert. So with ammonia, you've got to convert it into ammonia, and then you've got to convert it away from ammonia, and you've got to use catalysts and the extremely hazardous materials that you have to deal with. Where we don't want to touch any of those big processes, we want to actually look at, how can we just increase the efficiency of the existing compressed gas infrastructure. And so we're really targeting the gas blending market with ATCO, but also aerospace and space and heavy trucking. So Australia is a fantastic first adopter market for us to be in, and we've got some frenemies over in Berkeley, Mosaic Materials. Luckily, their materials are really water sensitive, so they don't operate in a kind of industrially relevant climate. So we're like, yes, we're the only ones. But there's a lot of other technologies, and they all have their place, right? So we don't see ourselves as directly competing. The whole market has to evolve, and every sort of technology will have its particular place for their particular need. So we're not going to really be that competitive in export, for example. So we've got a big team and rapidly expanding, and I'll move on to the panel because we want to get into some of the nitty-gritty of the discussion. But I just wanted to leave this up here. You know, hydrogen. This was posted by one of the think tank people from Agora, Annie Vande, about how fast the learning curve is for hydrogen. I mean, it's absolutely astounding how, you know, it's 21% per annum and getting much faster, right? So it's growing faster than solar, and so this is a very, very exciting space for us. But actually, we've got to go faster because it's where, yeah, you know, 2030. Everyone keeps talking 2030. Yeah, we actually probably got to do it more like 2027. So, yeah, very exciting times.
Great. Thanks. Thanks very much, Jehan. We've got a few minutes left for questions. So, Florian, I'll give the first question to you. What are the key challenges of hydrogen production, and do the same challenges apply to the space sector as other sectors?
Yeah, thanks a lot, Thomas. I think the challenges are quite different. Why is that? Look, if we talk about commercial space flights, it's a lot about emotions, perception, marketing. Rich people don't want to be ashamed in front of their mates to fly up there. And it's not so relevant if the price of hydrogen is $2, $3, $5, or $7 a kilogram. And that is very, very different if I look in the projects I've been working on with real companies and other use cases. And to understand that, we need to first understand where is hydrogen being used today? What are the applications? And people think of storing it and reconversion, long-term storages might be something for the future. What about mobility or blending it into the natural gas grid? Marginal amounts, small amounts. So it's definitely being used today as a feedstock. Where's that? What is that? Feedstock, it's being used to produce fertilizer, ammonia and stuff. And this is a typical B2B, business-to-business industry, and or for exporting. And these companies absolutely care about the question, is it $2, $3, or $5 a kilogram? So the challenges are a little bit different. And to make that, I see this in a lot of projects, like companies really care. They compare their options to decarbonize because they have to. And so the challenge really is how to bring the cost down. And I think there are 4 major things, like the regulatory framework, been a lot done on there. Second, the availability of cheap renewable power to produce real green hydrogen. Tick, prices really went down. The technology is available, it's technically feasible, but what we see is the ideal combination of these technologies, the overall optimization throughout the entire value chain. So that is a challenge in these projects.
Okay, great. Sorry, I was just a bit distracted there because the space gods have blessed us with an extra 10 minutes on our panel, right, as you can see. So,
yeah.
I want to, Wojciech, I think we're going to need to take a couple of minutes to explain the technology that you're talking about. So what you're describing is the usage of solar thermal instead of electrolysis to produce basically synthesis gas that can then be used in the existing aviation infrastructure. So it takes hydrogen, combines it with carbon dioxide, and then that is used as basically synthetic jet fuel. That's correct?
Correct. So this is an alternative route, and this is the less commonly presented route to produce solar fuels, we call it in our jargon. Basically, heat at very high temperatures is used to thermochemically reduce water and carbon dioxide to obtain hydrogen and carbon monoxide. Hydrogen could also come in this scenario from electrolysis because hydrogen is hydrogen. The issue is with CO2 splitting, as I mentioned. Once you build a thermochemical plant to split CO2 and you have similar thermodynamics of CO2 splitting and water splitting, it doesn't make sense to build another electrochemical plant for just hydrogen. Everything can be done using thermochemical technology. And once we have this solar synthesis gas, that's it, because the rest has been done over many years in the industry. Fischer-Tropsch process for basically syngas to any hydrocarbon, and the existing infrastructure, distribution, storage, turbines. I said that the turbines, jet turbines, this is the masterpiece of engineering. They have been optimized for efficiency because the temperatures of combustion in turbines are very high. The higher is the temperature, the higher is the efficiency, to the extent that I'm not sure how many of you are aware when you are flying that the temperature of flame in the turbine is above the melting point of the blades in the turbine. So I don't want to scare you, but this is the masterpiece of, we call it film cooling. There are very small channels in each blade that basically cool the materials below the melting temperature. So the reliability of those designs is an important another aspect. Now, as a solar fuel engineers, we don't deal with it. It has been solved. It has been optimized over many years by many companies, by academic research, by military research as well. And then we have the next issue that, again, we should pick up by research and development community and demonstrate, which is once the combustion is complete, CO2 is in the atmosphere, how can we harvest carbon back from the atmosphere? And there are competing routes. There is biomass route. It is basically the route that is very old, natural, and in many cases there is a progress in genetic engineering applied to biomass to grow it faster, to bind CO2 more effectively. But there are thermochemical processes at lower temperature, not at the temperature we produce syngas. These are typically hundreds of degrees of Celsius, where we can absorb CO2 and water from the air quite effectively with much higher efficiency than the nature does it when growing plants, and to provide concentrated CO2 stream. And in the near term, we have plenty of CO2 sources that should not go to the atmosphere at all. It doesn't make sense, for example, to emit CO2 from a cement plant into the air and then to pay the energy penalty to separate it again. Let's redirect in the near term all the CO2 streams that we already have to make synthetic solar fuels. Then we reduce at least the carbon footprint. We don't eliminate because depending on the source of the CO2 stream. There is steel industry, cement industry, and others. They will emit, they will keep emitting in the foreseeable future around the world. Maybe in developed countries, highly prosperous economies, this will be addressed sooner by electrification, by using renewable heat in the process industry. But still, there is a vast amount of cement factories, steel processing, steel factories where CO2 is emitted, and it will stay as is for some time, unless we do something. There are incentives to the economies that struggle.
Thanks, Wojciech. Yeah, no, good suggestions, good suggestions. I just want to jump over to Jehan before we lose too much time again. So can you tell us a little bit about how metal organic frameworks work, and where is the hydrogen going, and maybe how is it different to a metal hydride?
Yeah, so metal hydrides, it's probably easier to imagine that they're like batteries. They're metallic materials, and the hydrogen goes in and chemically bonds. So you actually don't have any hydrogen gas in a metal hydride. It's fully bonding and forming a lattice structure, a bit like in the way that an lithium ion goes in and forms a chemical bond in a battery. In metal organic frameworks, you have these. It's like more like a sponge. It's a big. You have large pores somewhere between. Very, very tiny pores actually, but they're very large from a chemist's perspective of 10 angstroms to 100 angstroms, so that's 10 to the minus 10 meters. And the hydrogen goes in and interacts with certain sites, and so over the years we've discovered that they interact with certain kinds of metals, and so we need to expose a certain surface of metals within that sponge framework. And so for us, our job is to actually increase the number of sites that there are in those lattice structures, and also increase the surface area. So we need to sort of optimize for a number of parameters. And we can do that both pre-synthetically before we make the material, or we can do it actually after we've made the materials. We can do various kind of modifications and tune the behavior to certain kinds of pressure ranges, because in dispatchable hydrogen, you might be using a 350 bar pressure system for a drone, which is work we're doing with Quickstep, or you might have a low pressure system like that AHK refueler, which is 30 to 40 bar pressure, and that actually, you have wildly different physics in those different pressure ranges. And in aerospace, we're seeing actually both room temperature, high pressure, and we're also seeing low pressure, low temperature, so liquefaction or versions of getting close to liquefaction without having to use liquid helium to actually do as an active coolant. So we need to actually optimize for very different environments.
Without going into too much detail, because you might not be able to talk about it, but you're working with Hypersonics, who is one of our member companies that I mentioned before, planning on using green hydrogen for their scramjets. What exactly are you doing for them? Obviously, without
they have a very interesting, without giving away. So they have a very unique set where they need to operate at room temperature. They need to have a flow rate just an unbelievably high flow rate. So they of about I think it's 100 grams per second. They need to be getting the hydrogen out of their system, and so that means, and they've got a total payload of somewhere between 10 and 20 kilos for their Mark II device. So we need to be able to operate very, very high flow rates, which is, there are no technologies out there other than metal organic frameworks that can deliver that. And you can't use liquefaction because liquefaction requires pumps, and that's too complicated. You just need to use passive pressure, and they don't have a lot of space. So it's a really interesting challenge to be able to get as much of that in there, and also then to get it out really fast. It's a really fascinating technology that they're developing up in Queensland, and very excited to be part of that program.
Yeah, it's been good having them as a member, actually. Yeah. Florian, I would like to ask you, and I know this is a bit of a difficult question for you to answer because you weren't directly involved with the hydrogen propulsion systems, but taking a step back, did you see the benefit of working in space projects for the development of Fichtner as an organisation? Was working on these more complicated projects, was the knowledge coming back throughout the organisation?
Yes, it was. Hydrogen's been around for quite a long time, and I often heard the question, why should it work out this time? We all heard about hydrogen 30 years ago, 20 years ago, 15 years ago, and then it got uncool, and now it's cool again. And we were in a very lucky position to work for the German Aerospace Center for actually, this is not marketing, 30 years, longer than my professional life. And we gathered and built up and could sustain knowledge in that field, doing engineering stuff in a, I don't want to say in a rather academic, also a bit protected area where we could build up this knowledge, which we are now using, dimensioning compressors, the entire hydrogen system, energy storage systems and stuff. So that was a great chance for us to build up and to hold that knowledge over a long time. We've got colleagues working in that field for a long time. Yeah.
Excellent. Yeah. Well, I mean, let's not go over time for the next half of the first panel. Do you have any closing remarks from maybe one of the questions we didn't answer in depth was, what is the need for this? The need for decarbonising the aviation industry?
Maybe I can give a very quick one.
Yeah.
Well, if we look at aviation, I think space is kind of a niche, but it is like a starting cell, and it's really an area where price is not so super decisive. As I said, if it's 2 or 5 or 7 euros the kilogram, it's not really these guys stopping doing things. But if we look at aviation, it already accounts for 3.5% of total human carbon footprint, like greenhouse gases. And this is going to massively grow. I just read about a number, a post-COVID number, assuming that this will triple or by the factor of 4 grow till 2050. So We'll see how that goes with Teams and all the virtual things. But there is a massive growth in this area, and it's very important to also, if we want to go carbon neutral, to also tackle this industry.
Absolutely, yeah, yeah. And there's many different propulsion systems that can be used for spacecraft, and I think Australia should look more into the usage of hydrogen or synthesis type kerosene, so that we can decarbonize our space sector and be an example for the rest of the world. And I think working with Germany is going to definitely bring positive benefits for that. So thank you very much to my distinguished panelists, and thank you very much for the extra time that we could have. And I think we'll vacate the stage so we can have the next half of the first half of the energy panel. Thank you.
Thanks a lot.
We go this way.
Thank you.